Welcome to this video lecture on data management. I would like to start off by showing the different steps in data analysis. The first three steps comprise the scope of data management. Now let us begin by first tackling data processing. To define what data processing is, it is a systematic procedure to ensure that the information or data that you've gathered are complete, consistent, accurate, and suitable for data analysis. And by that, we mean detecting and correcting or removing erroneous or inaccurate data from your dataset, a process that we call data cleaning. Data processing also involves organizing your data for analysis. It is an important necessary step you as a researcher will have to take to facilitate proper data analysis. Now, what actions are taken under data processing? The first is coding or inputting your data in the software. Next, you will need to check your data for any errors or inaccuracies. You'd want to know if all the responses given are reasonable or believable, if all relevant questions were answered, and if these given responses are complete. There may be a third step depending on the situation, which is the need to transform your data. Oftentimes, you may need to reconsider the different categories you've assigned a particular variable, and may sometimes need to make the decision of collapsing two or more categories into just one, something that is often driven by having many categories for a certain variable, but not having a big enough sample size to have good representation for each category. Another reality of research is the occurrence of missing data. One way of handling this is by employing imputation methods, something that requires statistical consultation and is beyond the scope of this video lecture. Continuing on, data processing involves three activities, namely data coding, data encoding, and data editing. Let's talk first about data coding. It is defined as a conversion of verbal or written information, preferably into numbers, in order to make your data more easily encoded, counted, and tabulated. Some examples would be assigning the number 0 for males and number 1 for females, or assigning 0 for a no response and 1 for a yes response. The purpose of data coding is to permit rapid and flexible storage, retrieval, and analysis of your data. Now, before actually starting the data gathering process, much consideration has first to be given to the nature of the data being collected, and the way in which this data can be coded should be thought through thoroughly as well. Now, before actually going to the field to collect your data, it is ideal to simulate the data collection scenario first with a small group of study participants, a process called pre-testing, to see if instructions in coding, as dictated in the coding manual, which we'll be touching on later, has been understood correctly by members of the research team. Now, let me introduce the different types of codes that can be used in the data coding process. These types of codes are namely field codes, bracket codes, factual or listing codes, and pattern codes. Field codes pertain to the actual values or raw information given by the respondents on the field. Now, this information is recorded as is by the researcher or the research team on what is called the source document. There should be a corresponding source document for each study participant. Now, examples of field coding include recording the age, weight, and height of study participants. Now, it is important to keep the original data that you recorded in the source documents and store these source documents in a secure place so that you can always go back to them to check for any errors or inconsistencies as you start the cleaning process of the data you encoded. Now, let's move on to bracket codes. These pertain to data that are recorded as a range of values rather than actual values. Now, the decision to record your data in terms of ranges of values generally depends on your research objectives, and you should have a valid basis for the ranges that you use. It is still highly recommended, however, that you record the actual value on the source document so that you can have something to look back at when you encounter errors in encoding. Now, let's use monthly income as an example. Earning less than 10,000 pesos per month can be coded as 1, while earning 10,000 to 29,999 pesos per month can be coded as 2, and earning 30,000 pesos or more each month can be coded as 3. Next are factual or listing codes. These are codes assigned to a list of categories of a given item or variable. Now, let's just say that the variable is civil status and has namely single, live-in, married, separated, or widowed in its list of categories. One way of coding each category on the list can be as what you see on your screens. Factual or listing codes can also be used when several combinations of responses to a question are anticipated, as what you would expect with multiple answer questions. Now let's use the list of symptoms of morning sickness as an example. The respondent can tick any of the symptoms in the list that she experiences. Alternatively, such multiple answer questions can also be handled with the use of pattern codes. Using the same example as previous, you'll notice that each symptom pattern is assigned a particular numerical code. Particularly in surveys or interviews, there will be questions in the questionnaire or interview schedule that are open-ended. These are questions that do not have pre-specified answers or choices, and invariably require more thought and more than a simple one-word answer. Just as with close-ended questions, codes should also be assigned to the answers before encoding. Thematic analysis is generally the method employed to come up with themes or categories of answers that arise as one sieves through the responses. However, thematic analysis is beyond the scope of this video lecture. Now, we make use of answers regarding the use of a certain food product as an example. In this case, let's just say two categories of answers or themes emerged, namely good taste and low price. The former has been assigned the numeric code of 1 and the latter 2. As you'll notice, there are variations in the way that each answer category can be worded and are grouped together accordingly. Now it is here where the importance of literature review comes in, because this is where you encounter literature that shows how answer categorization for similar questions has been done in previous researches. There are general rules that are followed when constructing codes. First, the research objectives and the use of the question in the analysis must be considered. Next, the codes should not be too detailed. For that matter, the number of codes must be kept to a minimum, preferably less than 8, and must not be too specific. To come up with categories for open-ended questions, it is justifiable to either perform a pretest and look for themes among the answers, or, if your study has a large sample size, you can do thematic analysis on the responses from the first 100 questions and come up with the answer categories accordingly. Next, codes should be exhaustive and mutually exclusive. And lastly, coding conventions should be adopted for questions with similar answers for consistency. Now, whether we like it or not, we may encounter problems with coding. That is, after all, a reality of research. One would be the problem of non-response to certain questions. Another would be the presence of questions that may not be directly applicable to particular respondents or study participants. For these issues, a suggested solution would be to adopt a coding convention to be used for the entirety of the questionnaire, wherein coding options are provided for no response and not applicable categories. Of course, if all else fails, always go back to the study participant or respondent in the field whenever necessary to obtain answers for questions they failed to answer. There are different steps in coding. The first will be to perform pre-coding activities wherein one lists and categorizes the responses. Answers to questions, particularly open-ended ones, are anticipated as well. Sometimes, the codes are already included in the data collection forms, which could be your source documents. Next, you'll need to develop what's called a coding manual, or a document which contains a record of all codes assigned to the responses to all questions recorded in the data collection forms. In other words, a coding manual provides instructions on how you are going to code the collected data. Of note, The codes to be used should be unambiguous. This is then followed by actual coding of responses. Now, these codes are written in the data collection forms. Now, this is an excerpt from a coding manual. You can pause this video so you can study the details in this table at your leisure. This is another example of a coding manual. Notice for certain variables that a code also exists for non-response. Now that concludes data coding. The next major activity in data processing is data encoding, wherein there is actual entering of the codes in a spreadsheet or data editor. Frequently used computer programs for encoding are Microsoft Excel, Microsoft Access, and EpiInfo. Microsoft Access is a database management system from Microsoft that combines the relational Microsoft Jet database engine with a graphical user interface and software development tools. EpiInfo, on the other hand, is a free downloadable statistical software for epidemiology developed by the Centers for Disease Control and Prevention, or CDC, that has data encoding capabilities as well. Conventionally, in a spreadsheet, the rows represent the study participants or respondents, or units of analysis if you're making use of, let's say, laboratory data instead of human respondents. A unit of analysis can be, let's say, a blood sample of a patient or something similar. The columns, on the other hand, represent the different variables being measured. Now, there's a particular type of spreadsheet that is used when investigating epidemics or outbreaks. This is the so-called line listing. Here, data from potential cases that appear throughout the course of an outbreak investigation are organized, stored, and analyzed. It allows information about time, person, and place to be organized and reviewed quickly, since time is generally of the essence in epidemics. Encoded data is basically the storage form of your data. It is important to store your encoded data because, for one, it is so that it allows provision for future access to explain or augment subsequent research. Data storage is likewise needed for evaluation or auditing purposes, particularly in clinical trials. Also, particular importance in data gathering in clinical trials, appropriate data storage is necessary as a safeguard against potential legal allegations. Now, how long should data be stored or retained? According to good clinical practice guidelines, in clinical trials, institutional review boards should retain all relevant records for a period of at least 3 years after completion of the trial, so that they can be made available upon request from regulatory authorities. This is a screenshot of a spreadsheet. The program used here is called Stata, which is a general-purpose statistical software package created by StataCore. Though not sorted chronologically, notice that the rows represent the study participants while the columns represent the variables being measured in each participant. This is an example of a line listing, lifted from the CDC website. It was constructed during an E. coli serotype 0157H7 outbreak. This features 26 students from a particular school who presented with symptoms of abdominal pain and diarrhea following a school event. Notice how the data is organized according to person, place, and time. And that is it for data encoding. Let us now move on to data editing, the third and final major activity in data processing. It involves the inspection and correction, and sometimes recoding of information according to a fixed set of rules. And this oftentimes happens concurrently with data encoding. It is during data editing where you check for the completeness and consistency of your data, and in the case of data written on the source documents, legibility as well. It is always best to make sure that your data is correct prior to encoding, because wrong data can become considerably difficult to detect once it already gets encoded in the spreadsheet, and this can lead to erroneous interpretation of your data. It is also imperative to ask yourself if your data is complete. Although imputation methods can be used, still, nothing beats going back to the source of your data, that is, your study participants, to collect the correct information. Now, we need to set the record straight that data editing is not synonymous to doctoring of your data. Data editing is important because you'll be able to make the necessary and appropriate changes or corrections to your data as early as possible. It reduces non-response or incomplete response since you'll often be going back to the source of your data whenever possible. Now, data editing likewise eliminates inconsistencies or incorrect or imprecise information. It is during data editing that you make data entries clear, legible, and comprehensible. Lastly, data editing prepares your data for analysis. As I sort of alluded to in the previous slide, whoever is editing the data must not change the original entries without verification from the data collector and without sufficient justification. Importantly, the editor must not destroy, erase, or make the original entries illegible. Any corrections the editor does should be marked in a distinctive color. Oftentimes, red ink is used. Each edited form must also be initialized and dated accordingly by the editor. Now, there are different types of data editing, depending on the point along the timeline of data collection and processing. In field editing, the accomplished data forms are reviewed generally by the data collectors themselves while still on the field. Now, this should be done as soon as the data have been gathered. Now, examples of such activity include decoding abbreviations, special symbols, and the like. Also included are making callbacks for verification and clarification of vague and incomplete answers to questions. Central editing, on the other hand, occurs after the questionnaires have been received from the field. Here, editors check for inconsistencies and incorrect entries. In this type of editing, inappropriate replies are replaced with the proper answers. To do so, the editors may often need to review the other information contained in the questionnaire. Central editing may also be automated with the use of a computer program that edits the data automatically and supplies the correct code. Sometimes, summary statistics such as means are used, particularly when assessing if a value of a certain continuous variable is an outlier or not. Now, here's one example. You're carrying out a study on the knowledge, attitudes, and practices of married couples with regards to birth control methods. You would like to assess the correctness of the data on the frequency distribution of sex in your study. In this study, you assign the value of 1 for male and 2 for female. You tabulate your data and see that a third category under the variable sex shows up. You know for a fact that this is an error in encoding since your coding manual only has 2 categories for sex. While someone from your research team is going through the source documents to look for the source of the error, you decided to make the software you're using execute the command of tabulating birth control pill use. You then see that 25 individuals answered not applicable to that particular question, which would make you think that those who answered it as such are most likely males. Comparing it with the frequency table on sex, you see that there are 25 males in your sample. That perhaps gives you stronger evidence that the lone study participant with a code of 3 for sex is most likely female. Eventually, you did confirm from the source documents that this respondent is indeed female. This turned out to be just an error made during the encoding process, which you have now rectified. We go back to this spreadsheet from earlier. Pause the video and take time to breeze through the dataset. Do you notice anything unusual? If you notice these numbers, then you are correct. You command the software you're using to supply you with summary statistics of the continuous variables in your dataset. You see that your sample of 101 participants are basically all adults. However, you see that the minimum weight of your sample is just not possible for a normal adult, unless an individual has a condition resulting in short stature, which would account for the height of 50.2 centimeters as well. But then again, even that height is too short. Of course, you cannot just make assumptions, and it is imperative that you go back to your source documents to see if this was just an error in encoding. Using the identification number of the respondent with the height of 50.2 centimeters, you were able to retrieve the source document and saw that the weight of that respondent was actually 44 kilograms instead of 441 kilograms, and the height was actually 150.2 centimeters instead of 50.2 centimeters. Now, as for the individual with a weight of 28 kilograms, it was found in that person's source document that the weight was actually 78 kilograms. The number 7 was mistakenly encoded as 2, a product of human error. And that concludes the portion on data processing. We now proceed to the next step in data analysis, which is examining your different variables. The topic on variables is actually handled in more detail in a different video. For this video lecture, we are just going to do a quick review. Variables can be classified according to type, namely qualitative variables and quantitative variables. Qualitative variables, also called categorical variables, are variables that are not numerical, but rather describes data that fit into categories, like sex for instance, which is either female or male. Quantitative variables, on the other hand, are variables that are measured on a numeric or quantitative scale. Such variables can either be discrete or continuous. Discrete quantitative variables can only take on a finite number of values, typically as integers or whole numbers, while continuous quantitative variables have an infinite number of possible values, and they generally involve numbers with decimals. Variables can also have different levels. A nominal variable is actually another name for a categorical variable, and they have 2 or more categories without having any kind of natural order, unlike ordinal variables, which are categorical variables for which the possible values are ordered. Interval variables, on the other hand, are variables whose values have constant equal distances between them, like with temperature, for instance, which follows an interval scale. With interval variables, the 0 point is arbitrary, which means that the value of 0 does not mean the true absence of something. Lastly, ratio variables are variables that have the same characteristics as interval variables, only this time the 0 point is actually meaningful and not arbitrary. That is, the value of 0 actually means the true absence of something. Variables can also be classified according to causal relationship. You have the independent variable, which is sometimes called predictor variable. There's also the dependent variable, which is known as outcome or response variable, and is dependent on the independent variable. We can also have intermediate variables, which are variables through which the independent variable exerts its effect on the dependent variable. Now, regardless of what type or level of variables you have in your dataset, it is imperative that you always check and make sure that you understand and are well acquainted with the nature of your variables prior to data analysis, so as to know which appropriate statistical test or method of analysis to employ accordingly. Now, part of data management is summarizing your data in presentable forms using tables and graphs. Now, this is where descriptive statistics come in handy. As a review, descriptive statistics involve techniques for summarizing and presenting data in a form that will make them easier to analyze and interpret. Very often, univariate statistics are employed. They represent the simplest form of data analysis, and as the name implies, they involve only one variable. And because only one variable is involved, there are no comparisons with other variables to analyze relationships, associations, or causation. Univariate statistics are generally just there to give you a feel of your data. Now, as I mentioned earlier, we can present data in the form of tables or graphs. We will be delving into that more in a minute. In a nutshell, univariate statistics are composed of counts, ratios, proportions, and rates, measures of central tendency, measures of dispersion, and measures of position. The first is quite self-explanatory. They are essentially frequencies and percentages. Measures of central tendency include the mean or average, median or middlemost value when the array of numerical data is arranged from highest to lowest, and mode, which is the value that occurs more often. Now, measures of dispersion include the range, or simply the extent between the lowest and highest value, variance, the measurement of spread between numbers in a dataset, standard deviation, which is the square root of the variance, and the coefficient of variation, another measure of data spread when comparing the degree of variation between two different variables. Finally, we have measures of position, which indicate or identify the position that a particular data value has within a given dataset. Under measures of position are quartiles, which divide an array of data into 4 equal parts or quarters, deciles, which divide a dataset into 10 equal parts, and percentiles, which divide a dataset into 100 equal parts. Now, as promised, we will talk about tabular and graphical presentation of data. Now, let's start off with tabulation by talking about dummy tables, which are essentially tables which have the proper parts, that is, the title, column headings, and row headings. The only thing is they do not contain data. Now, dummy tables represent the actual tables that will be in the findings section of the final report. They are used to provide a better understanding of what the actual outcomes of the research will be, all in preparation for data analysis. Now, by using dummy tables, you as researcher are anticipating what your final research report will contain, table by table, before the project even begins. Now, they help you visualize your data in relationship to your theory, your data gathering methods, and the hypothesis you hope to support. Now, here's an example of a dummy table. Now, among the researchers' objectives in this project was to describe two particular groups, namely those who experienced extubation failure and those who did not, in terms of medical and surgical comorbidities. Here, he would like to tabulate the frequency of those with hypertension, coronary artery disease, etc. for each group, and compare the percentages using the z-test to see if they are significantly different from each other. How tables are presented also depends on the number of variables being described in a table. When counts are classified according to a single categorical variable, then that table is said to be a one-way table. The counts across the different categories of that variable are presented in only one column. The purpose of one-way tables is to simply describe the profile of the sample you studied, or to describe the prevalence of a disease or condition, for instance. Two-way tables involve two categorical variables. The counts in one variable are organized in columns depending on the number of categories for that variable. The counts in the other variable, on the other hand, are organized in rows, again depending on how many categories that other variable has. Two-way tables are commonly called contingency tables, and since with two-way tables there are two variables involved, these tables are used for purposes of comparing these two variables and seeing if an association exists between them. Lastly, we have three-way tables. In these tables, there's a third variable whose categories can serve as levels or strata for the first two variables. Three-way tables are basically two-way tables that are combined according to categories of a third variable. If with two-way tables we investigate association between two variables, with three-way tables, we investigate if the third variable acts as either a confounder or an effect measure modifier to this association. Now, the next few slides will show examples of these three types of tables. Now, this is an example of a one-way table. The variable involved here is age group with the following categories. As you can see here, the frequencies for each category are all listed in a single column. This is a two-way table. Notice that the two variables involved are handedness, with its three categories each represented in a column, and sex of the child, with its two categories each represented in a row. Here is another two-way table. This time, the two variables involved are oral cancer, whether it is present or absent among the included study participants, and alcohol intake status, whether the study participant is a drinker or not. Now, this is an example of a three-way table. Notice that there are three variables involved, namely delinquency, either yes or no, Scout membership, also either yes or no, and socioeconomic status, the categories of which are low, middle, and high. Notice as well that there is a series of two-way tables, combined according to categories of socioeconomic status. We now go into graphical presentation of data. In this manner, data is presented using graphical symbols such as lines, bars, pie slices, dots, and the like. We will go through examples of these in the slides that follow. This is an example of a bar graph. Here, the number of immigrant students at a particular college are presented as counts per country of origin. The x-axis is the number of immigrants, while the y-axis shows the different countries of origin arranged in alphabetical order. Since the counts increase from left to right, the bars project to that direction as well. Bar graphs are used for comparisons of absolute or relative counts, rates, or percentages between categories of a qualitative or a discrete quantitative variable. Now this is another example of a bar graph, which presents the number of students using internet at a particular secondary school from 1995 to 2002. The bars are oriented vertically instead of horizontally, as in the previous example. Notice that for each year, the number of students are stratified according to sex, meaning there are separate bars for boys and girls. This is an example of a pie chart. All parts of the pie, when summed together, should always total 100%. Pie charts show the breakdown of a group or total, and is appropriate to use when the number of categories is not too many. That is, for around 6 categories or fewer. This is an example of data presentation using component bars. Also called subdivided bars, component bars function very much the same way as pie charts, only that bars are used in place of pies. Notice how the components of the bar total to 100%. Now this figure here is what's called a histogram. Histograms are similar to bar graphs, only that histograms group numbers into intervals or bins. In the case of this example, the systolic blood pressure readings are grouped into intervals that appear to be 2 millimeters of mercury wide. Now, the height of each bar represents the frequency, or how many individuals fall into each interval. Histograms are useful when you would like to give a graphical representation of the underlying frequency distribution of a continuous variable or measurement. Now, data can also be graphically presented as frequency polygons. They function similarly as histograms, but the difference here is that frequency polygons are constructed by using lines to join the midpoints of each interval. Just like with histograms, the height of the points represent the frequencies. So here's another example of a frequency polygon, but superimposed this time to its corresponding histogram, to facilitate clarity of what I just explained in the previous slide. This next one here is called a line graph. Basically, line graphs, which are sometimes called line charts, show trend data or changes in a particular variable with time or age. That being said, the x-axis is typically time, while the variable whose trend is being assessed or tracked is in the y-axis. This example here shows the trend of overweight and obesity in the Philippines over several years. You will notice that for certain age groups, the line graph does not extend all the way back to 1989, probably because it was only in later years when information in these age groups was only started to be collected. So the x-axis here is time in years, and the y-axis is a proportion or percentage of overweight and obesity. Now this here is what's called a scatter plot. Now scatter plots are plots that make use of Cartesian or xy coordinates to display values for typically 2 variables. Scatter plots are basically used to show correlations between 2 quantitative continuous variables, that is, how much one quantitative continuous variable is affected by the other quantitative continuous variable. Now sometimes a best-fitting line, or the so-called regression line, is graphed as well to represent the overall relationship between the 2 quantitative continuous variables involved. Now this table summarizes the different types of graphs, the kind of variables each graph type is applicable to, and the function of each type of graph. You can pause this video so you can take time going through the information contained within. And that ends this video lecture on data management. Now, data management basically covers the first 3 steps in data analysis, which were discussed at length here. The remaining 3 steps will be covered under data analysis itself, which is a separate video lecture. Thank you and good day.